Today we're going to discuss how to multiply two matrices, two n by n matrices, and we're going to think about the running time of this algorithm. There's a basic algorithm which you probably learned in high school, which simply involves taking the dot products of the rows and columns of x and y in the appropriate fashion. It turns out you can use a divide and conquer strategy as well that ends up giving you a recursion, and we can try to estimate the running time of that recursion using the master theorem. The first attempt we make at this is actually not going to be any faster than the standard O of n cubed algorithm, but there's a little trick similar to the trick of Gauss, which is going to save us one recursive call, and that's going to improve our algorithm a little bit and get us below n to the 3. Let's see how that works. Okay, so now we're going to think about how to multiply two n by n matrices and what the standard algorithm is for doing that. So here we have these two n by n matrices, x and y, right? They're both n by n matrices, and we're going to multiply them together to get z, which is also going to be an n by n matrix. Okay, so what's the algorithm to compute this matrix z, right? Let's think about the algorithm we need to compute the entries of this matrix. Okay, so think about computing, let's say, the zijth entry of this matrix, right? Zij. First, we would have to initialize zij to be 0. Then we have to sum over k, and we're going to have to take the dot product between this row of x matrix and this column of y matrix, the ith row of the x matrix with the jth column of the y matrix. We take the dot product between those two, that row and that column, and then that's what gets entered into zi for a zij. So you'll see here I'm computing that by doing zij starts out as 0, and then zi for every k in the range of n, zij, we add to zij xik times ykj. That's a way to compute the dot product between this row and this column. Of course, this is just for a single entry of the matrix. We would have to loop over all possible entries in this matrix. So I'm going to have to take a for loop for every j in range of n, and of course for every I in range of n as well. So I'm going to have to do this for every single ij entry of z. I'm going to have to do this computation. So what's the running time of this algorithm? Well, you'll notice that we're going to have n iterations here. We're going to have n inside of that. We're going to have n iterations here, and then of course we're going to have n iterations inside that, right? So we have 3 nested loops, each of which is going to take n iterations. So the running time is equal to on the order of n cubed. You'll notice that every time once we get inside of these 3 loops, the only operation we have to do is this one, and that's an order O of 1 time operation, right? It involves multiplying 2 real numbers and adding that to zij. So in total, the total running time is on the order of n cubed. Okay, so now what we're going to do is try to solve matrix multiplication using a divide and conquer strategy. Okay, so we're going to assume that n, which is the size of the matrices, is a power of 2. And we can always do this without loss of generality, because if it were not a power of 2, we could simply round n up to the nearest power of 2, and then just fill the rest of the matrix in with zeros, let's say, and then compute this on the compute the product of the larger matrix, and then extract the answer from the submatrix. So there's always a trick to do this. It just is convenient to assume that it's a power of 2, and there's ways around it when it's not a power of 2. Okay, so we're now going to write our matrix x and y as each in block form. So we're going to take x and break it up into an n over 2 by n over 2 matrix A, B, C, and D. Right? This is we're just basically breaking the matrix up into 4 blocks of equal size. We're just going to write it as a bunch of submatrices. And if you now look at the product x times y, what does the product x times y equal to? Well, it turns out you can write this as sums and products of these smaller matrices. So this is going to end up equaling A times E plus B times G. Down here is going to be C times E plus D times G. Over here we're going to get A times F plus B times H, and down here we're going to get C times F plus D times H, right? And we can now write x times y in this form. So you can see that this immediately suggests a recursive algorithm. To multiply x times y, we simply have to take x and y, break them up into smaller block matrices, into smaller submatrices, and then multiply those submatrices together. Of course, when this recursion gets down to matrices of size 1, well, then you're just multiplying numbers together. The way that you combine the results of those recursive calls is exactly like this, right? You would recursively multiply a times e and b times g, and then you would add those matrices together to get the top block, and so on and so forth. So this gives us a natural divide and conquer type algorithm by reducing the product of these two n by n matrices to a bunch of smaller matrix multiplications on the order of n over 2. So let's just address one thing first. You'll notice that we have these 4 additions here, where you have to add two n over 2 by n over 2 matrices together. So I'm going to say that these additions each take on the order of n squared time. Okay, so to add two n over 2 by n over 2 matrices together, you simply have to, the only way you can really do this is by essentially looping over all rows and columns and simply adding the items in each matrix together. And you can see that's going to be an n squared type, an O of n squared type algorithm. Let's think more about the recurrence relation. So the recurrence relation for the whole algorithm is going to be t of n equal to, notice that we have to do 8 different multiplications. 1, 2, 3, 4, 5, 6, 7, and 8. Right? We had to do 8 multiplications to get each of these to complete this algorithm, and so we're going to have the number 8 of these things. Each multiplication is on a matrix of size n over 2 by n over 2. So we have a subproblem which is on the order of n over 2, plus, as we said, an O of n squared time to add these products together in the appropriate fashion. Okay, so let's now think about the master theorem and how we can use the master theorem to actually solve this recurrence right here. You'll notice that in the master theorem you have, this is like a times n over b plus O of n to the d. Well, now we know what a, b, and d are. So a equals 8, b equals 2, and d equals 2. Remember that to use the master theorem you have to check what is a over b to the d. In this case, a over b to the d is 8 over 2 to the 2, and that's strictly greater than 1. And when that's strictly greater than 1, we know that the third case of the master theorem is the important one. Okay, just to remind everyone, this was the master theorem. This is the case that we are interested in, this third case right here. We had to check a over b to the d. That was strictly larger than 1, in which case we're going to get a running time of O of n to the log base b of a. So let's go back and look what that ends up meaning. Okay, so in this case, we know that we're going to have t of n. Using the master theorem, we have t of n equals O of n to the log base b of a, which equals O of n cubed. Why n cubed? Well, log base 2 of 8 is 3, so we end up getting an O of n cubed algorithm. Now you'll notice that this divide and conquer algorithm isn't faster than the algorithm we tried previously. We had a very direct algorithm where we simply tried to compute every entry in the matrix Z by just taking the dot product between the corresponding row and column from x and y. That was an O of n cubed algorithm. This is also an O of n cubed algorithm. We didn't get anything faster, unfortunately, for this divide and conquer strategy. Okay, now I just want to briefly mention a fact which is very cool. It so happens that that last algorithm, divide and conquer algorithm that we discussed, there actually is a faster version of that. You just have to be a little bit smarter. There's this amazing trick, and I don't know who observed this first, but it's a very impressive fact, and it really comes from the same idea that Gauss had when it came to multiplying complex numbers. It turns out that if you write your matrix x and y in the same block form, right, a, b, c, d, e, f, g, h, in the same block form as before, it turns out that you can write x times y, right, as a block matrix which combines not 8 multiplications but 7. Here are the 7 products, P1, P2, P3, P4, P5, P6, P7. I won't go into detail about how you get them, but if you work out the algebra, if you take these 7 matrix multiplications that are written here, and you combine them in the way that they're combined here, you'll actually get exactly the same thing as we got before, but you'll notice that this time we only needed to do 7 matrix multiplications. We do have to do some more additions and subtractions here. You'll notice that we have to do, for every one of these products, there is an addition in there, sometimes more than one. And of course, up here we had to do more additions and subtractions, right? But each of those additions and subtractions, there's only a constant number of them in total. And so the total number of adding and subtracting is still on the order of n squared. So we're going to get exactly the same running time except for one fewer multiplication. So let's write it out. If we sort of follow this newer divide and conquer strategy using fewer multiplications, we would have t of n equals 7 times t of n over 2 plus on the order of n squared, right? And let's just write out, we have a equals 7 now, b equals 2, and d still equals 2, right? We have a over b to the d, just to use the master theorem. That equals 7 over 2 squared, and that is, that's between, it's 1 3/4, which is still larger than 1. So we end up being in still the last case of the master theorem. So we know that the final running time is t of n equals O of n to the log base 2 of 7. And if you're curious, log base 2 of 7 is roughly speaking 2.81, right? 2.81. 2.81 is still smaller than 3, so we actually now have a faster algorithm. It's not on the order of n cubed, it's on the order of 2.81. And that's cool. I should just emphasize that when this trick is used to do matrix multiplication, we call this the Strassen algorithm, right? It's a very well-known algorithm for matrix multiplication. And by the way, this is mostly the only algorithm that's really used in practice. There are faster algorithms for matrix multiplication, but they tend to be only theoretically faster, and you'd have to have very large n for them to actually be faster in practice. Let me just finish with a couple of interesting notes. The problem of matrix multiplication is actually a very interesting one in computer science because it's still not even known whether you'll be able to get something down to us on the order of n squared. It could be that there is an algorithm that's on the order of n squared for matrix multiplication, we just don't know. Up until 2010, the fastest algorithm was called the Coppersmith-Winograd algorithm. And that has a running time of n to the 2.376. It was improved to O of n to the 2.374, and I think a little bit later, I think in 2010, it was improved to n to the 2.373. And I'll just mention this because I remember when that happened. When I was in grad school, Virginia Vasilevska ended up improving upon this result just a little bit to shave off just a tiny factor from that exponent. So as you can see, we're still really chipping away at this problem, and it's apparently a very challenging one.